Okay, guys, I think it is time for us to start. We almost waited for 8 minutes. I think it might be a good idea to start.
Sounds good.
Okay. Okay, guys. Which question you want to start with?
I had a question on number 15 and 11.3.
Okay. Fifteen and 11.3.
I think it may be because I'm not totally clear on unilateral connection. I think I got 14. But
Can you tell me what is your argument in 14?
I said if a digraph has no isolated vertices, the digraph is connected. And so for any two vertices, W and V, it is possible to find a path leading from W to V. Since this graph has a Eulerian closed path, every in degree and out degree for each vertex is equal. Thus, if you follow the Eulerian closed path, every vertex and every edge will be traveled on. Thus, the graph is strongly connected.
Okay, you almost got the right idea. I think the way normally you can say it is, if you want to be more precise, if you want to show this graph is strongly connected, I hope others can hear me as well. If you want to show the graph is strongly connected, the thing you need to show is, if you close your eyes and pick any two vertices, I can go from one to other in both directions, right? So the way you need to say it is, this is a digraph, and they are saying it has a closed Eulerian path. Maybe I'll call that path as P. So take any vertices in U and V, and since that is an Eulerian path, both the vertices should belong to that path, right?
Yes.
So you take, suppose you want to go from U to V, you pick out that path, Eulerian path, and start at U and keep going in that path until you hit V. You know you are going to hit V at some point because it is an Eulerian path.
Right.
And if you want to go from V to U, you will come back the other direction. You will just start at V and come back. So this is possible because it has a closed Eulerian path, right? If it is not closed, then it is not guaranteed, because you might go from one direction, but it might not be able to come backwards if it is not closed.
Right.
That's what happens in 15. I think you got the idea correct. I think maybe just writing sentences the way I said it might be more easier for to read, I guess. But the way you can do it in 15 is, now you all can see the PowerPoint, right, guys?
Yeah.
Okay. So 15, you can say this. Again, first almost the couple of sentences, whatever you had drawn for 15, I think will work as well. But the only difference in 15 and 14 is, when it comes to 15, it is not guaranteed you can go up in both directions, because this is not a closed Eulerian path. It is just an Eulerian path, right?
Right.
So again, you can say this. For example, this is your graph, and you know it has an Eulerian path. That means you can start at a point and visit each and every vertex, each and every edge, I apologize, or arc, whatever you'll call it, so that you can cover everything. Am I making any sense?
Yeah.
So take any two vertices, let U and B be any two vertices in D. Hope you all can see my handwriting here. Now it has a Eulerian path. Let P be the Eulerian path. When you say that is an Eulerian path, it starts at a point and visit each and every arc and ends at some point, right?
Right.
So you start following the path, you will either hit U or V, one of them first, right? Because you are going to hit each and every edge. So that
Right.
means you're going to hit each and every vertex. So certainly you will either see or U and V, both of them you will see, right?
Mm-hmm.
So suppose you see U first. Let U be the first vertex you encounter between U and V I am talking about, because you already picked your two of them, and you need to show I can go at least from one to the other. May not be both or maybe both, I don't care, but at least if you can show you can go from U to V or V to U, you're good. Am I making any sense, Chelsea?
Yes.
Let's say U be the first vertex between U and V. I'm wrong. Let U and V. Let U be the first vertex among U V, among U comma V. I mean, you might see so many of them, but suddenly U is the first vertex you encountered. Maybe again, I'm writing in my own words. You can write it in your own words, okay?
Mm-hmm.
Encountered in P. Then start at U. Then take that portion. So you suppose you saw here. Now you keep on going until you hit V, and take that portion in P, and that portion is going to give you a connection between U and V, right?
Right.
Yeah. Start U, follow P until you reaches V. Until you reach V. Now take that portion of P. Take that portion of P, which will give a connection between U and V, which will give a path between U and V, which will give a path between U and V. And I don't care about the other direction because I know I showed you can go from one to the other. That is good enough. Man, my handwriting is all over here. So hence D is unilaterally connected. So the only difference between 14 and 15 here is I'm telling you where to start. Whichever the one you first see,
Okay.
that is your starting point, and you are going to go to the other for sure.
Okay.
Is that making sense, guys, for the other people I'm talking about?
Yeah.
Okay.
Sure.
Maybe if you are noting it down, I will give a minute. I am sorry, my handwriting, I'll try to be more neat next time onwards, but I'm just saying.
So I have a question.
Yes, sir.
So the only difference between 14 and 15 is you're talking about a closed path. Therefore, you can get from U back to V if it was just kind of a cycle.
Yes, exactly. When it comes to this, in 14, you can say you start at U. Man, where is my pen? And you keep following until you hit V. And since it is a closed path, you can again go from V and follow this and go to U.
Right. So since it's
Yeah.
not closed, then there's no guarantee that you can go back from V back to U.
Exactly. Exactly.
Okay.
Okay, I'll come down a little bit so you can copy it down if you guys something. Again, you can write it in your own words. Really, there is no reason that you have to write the exact same words I'm just writing here, but you can write it in your own words. Okay. The next question, guys. If you are done noting it down, if you are noting it down, just don't worry about it. Please follow on. Okay, that's it. You have any other questions? Again, since I am using the PowerPoint, if you type something I cannot see in the chat session, so please speak out if you can. I really appreciate that.
We go over 11.5.19.
Okay. Oh, 11.5.19. You have any questions in the middle, guys? The rest, the other two folks.
I haven't got to 11.5 yet, so those were two questions that I had, but.
Okay, I will talk about 11.5.19 then.
I've just briefly looked at 11.5, but like looking through the questions, I would seem to have trouble on the proving and showing problems. So
Sure. I am going to give you the complete idea, but you can write it in your own words, right?
okay.
Okay. So 11.5.19 again. Just to give you broad for the other two as well. You know the difference between Eulerian and Hamiltonian, right? So Eulerian circuit means you start at a point and visit each and every edge and comes back to the same point. When it comes to Hamiltonian, you start at a point, visit each and every vertex. Now I don't really care about edges. So I think you all know that difference. I think at least I'm hoping you have seen the videos there.
Yes.
So for example, if I take this graph, I can start here. This is A and this is B and this is C. So A, B, C, A. This is an Eulerian circuit, right?
Yes.
Similarly, that is a Hamiltonian circuit as well because I visited each and every vertex also. But if I just remove one of the edges, A, B, and I'll say C, now this has no Eulerian circuit because I cannot start and end it at the same point, but it has a Hamiltonian. Oh, it doesn't have a Hamiltonian circuit as well. I'm sorry. Let us put one more here. Say I'll call D. This has an Eulerian circuit A, B, C, A, but it has no Hamiltonian circuit because I cannot touch D. Right? This is a graph which has an Eulerian circuit but no Hamiltonian. This is one of the questions in the previous assignment problems. So people think Hamiltonian might be a little bit easy because you don't need to visit each and every edge. You are just touching the vertex, that is good enough. But finding Hamiltonian is a much more difficult problem than Eulerian. This is called an NP-complete. That means there are problems in mathematics which are called NP-complete. That means nobody knows whether they are right or wrong. If you can prove one problem is right, then everything else is right. If you prove one problem is wrong, then everything else is wrong. For example, prime factorization is one of the NP-complete problems. That means if I give you a huge number, can you break it up into product of two numbers as each one of them is a prime? People say you can do it, but nobody knows whether actually you can do it or not. There is no procedure. These are all NP-complete. That means these are pain in the neck. These are very difficult problems. But for Hamiltonian, for Eulerian, there is an if and only if condition. So you can look at the graph and you can easily tell whether that is an Eulerian circuit or not without even thinking about it, if you know the result. But for Hamiltonian, there is no result like that. All are only sufficient conditions. That means you look at the graph. If the graph satisfies those conditions, then it has a Hamiltonian circuit. If the graph doesn't have an Hamiltonian or satisfy the conditions, it might or might not. You never know. So there are a bunch of sufficient conditions. That means you look into the graph, and okay, graph satisfies all these properties in that particular theorem. So you can conclude that graph is a Hamiltonian circuit. Suppose it doesn't satisfy, then you cannot say anything. Then you have to see is there any other reason works. You might be thinking, why the hell we need to do that? Can't we just look into the graph and figure out? The problem is a good percentage of the graphs in realistic applications have like 5,000 vertices and 15,000 edges. For example, all the airports in the United States, you can think of them as vertices. And if there is a plane connection, you can think of that as an edge. So entire airlines connection is a huge graph. If you want to figure out that one has a Hamiltonian circuit, that means if you want to start at a city and visit each and every city and comes back to the same city, can you do that or not? That is an NP complete problem. Nobody knows. Am I making any sense, guys?
Yeah.
And so one of the sufficient conditions is theorem 11.10. Theorem 11.10 on page 662 says is this. Again, this is for the digraph. If you have a digraph something like this, again, I'm not sketching the graph. Take any two vertices. I'll say X and I'll say Y. These are non-adjacent. That means they are not directly connected by an edge, by an arc. I should say arc because it is a digraph. Then, if the out degree of X, that means the number of arcs which are leaving X, plus in degree of Y, if you add them, if that is greater than or equal to the total number of vertices, then you will say the graph is Hamiltonian. The proof is beyond the scope of the book. That means all it is saying is it has too many arcs. Then there are more ways you can go from one point to the other, so it is Hamiltonian. That is the underlying assumption. The out degree, the number of arcs leaving X and the number of arcs coming in Y, if you add them, that is bigger than the total number of vertices. That means it has many choices for you to explore, so it is Hamiltonian. That is the logic behind it. Am I making any sense, guys? Can you hear me now? Okay, I'll assume you can hear me. So for problem number 19, what they were saying is this. Take any two vertices, X and Y. The out degree of X plus in degree of Y, suppose that is greater than or equal to n minus 1. That means it is not n. That is in theorem 11.1, 10 says it is n. That is on page 662. Now suppose instead of n, if I say n minus 1, that means it is 1 less. Then you need to prove it has a Hamiltonian path, not circuit. If it is n, you can start at a point and visit each and every vertex and comes back at the same spot. Suppose if you take one less, then the result is saying you need to prove I can start at a point, visit each and everything. You might not end up at the same spot, but you should be visit each and every vertex. That is what you need to prove. So we need to prove D has a Hamiltonian path, not circuit. That is what you need to prove. Am I making any sense, guys? So that is what you need to prove. So I am going to explain the proof now. I'm going to give you the idea. You can write it in your own words. The proof goes like this. You have a graph. I'll call that as D. Again, I'm not sketching the graph. D is the graph given to you. And you know for sure, take any two vertices which are not directly, which are not adjacent. That means there is no arc from X to Y. Then if you know out degree of X plus in degree of Y is greater than or equal to n minus 1. You know that. Take any two vertices, if there is no arc between them, then out degree plus in degree is greater than n minus 1. Then you need to prove I can start at some point and visit each and every vertex and end at some other point. But you should be able to visit each and everything. Now what I'm going to do is I'm going to construct a new graph. There is a hint on the back of the book. If you look into that, that hint really explains pretty well. Construct another graph. I'll call that as D1. All I'm doing is I'm adding one more vertex. I'll say U. And what I'm doing is in D1, I'll take the entire D and also I'll add some more arcs. What I do is take U and take each and every vertex in D. And I'm going to add like this. That means I need to add an arc from U to each and every vertex in D, and also I need to add an arc from each and every vertex in U, D to U. Is that making sense so far? So this entire thing is graph D, and I'm adding one more vertex, and all I'm saying is I am connecting that vertex to each and every vertex in the original graph. That is my D1. Am I making any sense, guys?
Yep.
Now for a D1, if you see the out degree of X plus in degree of Y, because U is connected to each and everything, so this X and Y cannot be U, because this X and Y has to be non-adjacent. So this X and Y, you know, cannot be U. Then that is greater than or equal to N. Do you agree with that? Because for each and every vertex, I am adding one arc going out and adding one arc going in. So the out degree and in degree both goes up by 1 in D1. So in D1, out degree of X plus n degree of Y greater than or equal to N. So for D1, I can use theorem 11.10. D1 has a Hamiltonian circuit. So that means in D1, I can start at a point and visit each and every vertex and comes back at the same point. In D1, I can do that. Since this is a circuit, I can start and visit each and everything and comes back at the same spot. I can assume I'm starting at U and ending at U. I can do that, right? Because this is the circuit. So instead of starting at any point, I'm assuming I'm at U and visit each and everything and ending at U. I'll call that Hamiltonian circuit as, say, maybe C. Now in C, what I'm going to do is I am going to remove U from C. So remove. So whatever is the vertex I added, I removed it again. Once I removed it, the only vertex that is going to go away is U, and the only arcs that is going to go away are the ones which are going out of U and coming in U. That means those are the ones which are I added later in D1. So then C minus U will contain all the vertices of D. So C minus U is a Hamiltonian path. It is not a circuit. I'm sorry, my handwriting is not great here. It's a Hamiltonian path in D. Am I making any sense? So you have a digraph. This is a digraph. And you know out degree plus in degree is greater than n minus 1. So you use that, you construct a one more digraph called D1. All you do that is you add a vertex, and this vertex is connected to each and everything in D in both sides, both ways. So from U to X and X to U, U to Y and Y to U. So now in D1, I can use theorem 11.10. I know it has a Hamiltonian circuit C. Maybe this is my circuit C. In C, I will take away U. That means U is gone, and all the arcs that are attached to U are gone. That means only two of them are gone. So C minus U is a Hamiltonian path in D, because C minus U has all the vertices in D and all the arcs are also in D. So I got my Hamiltonian path. Is my explanation making sense, guys?
Yes.
Okay. You can write it down in your own words. Again, I know I was all over here, but I don't want to write a very formal proof for you. You can write it down. But just that's it. It's not like more than 4 lines or something. You don't need to write too much explanation.
I just have a quick question about 15 in that same section. Do you want us to write a proof for that, or do you want us to give an example?
15 on
15A?
oh 11.5.
Yeah. It asks us to show that G is a Hamiltonian circuit. So do you just want us to like show it by doing a graph, or do you want us to show it by cubing?
They already have given you a graph. I don't think you can draw a graph there. But sketching the graph is a pain in the neck for that. So all you need to do is just one line answer. For 15A, I'm talking about, let me insert a new slide. Blank slide. Okay, if you look at the pans, you can say, I'll call that as G has n equals to 11 vertices, right? And degree of each and every vertex is 6. If you want to sketch this graph, it is going to take a lot of time for you. So here you can use Orr's theorem. Theorem 11.8 says is this. Take any two vertices. If you add those 2 degrees, then that is greater than or equal to n, then it is Hamiltonian circuit. So you need to write, it's a proof is a big word to use. You can simply say this. Take any 2 non-adjacent vertices. That means these 2 vertices are not connected, x comma y. Then add those degrees, degree of x plus degree of y. What is degree of x? You know that is 6, because degree of each and every vertex is 6. Degree of y is 6. So I'm sorry, this is exactly equal. So this is going to be 12, and that is greater than or equal to 11, right? Because that is your n. So degree of x plus degree of y is greater than or equal to n. So by theorem 11.0, G has a Hamiltonian circuit. That is all you need to write.
Okay, thank you.
Sure. Don't try to sketch the graph. That is going to be a huge headache. Any other questions, guys? Okay, I think you're chatting. Let me go there. Let me. Oh, you can't get the microphone. Okay, I'm sorry. I need to come back there and check. Okay. I can't get the microphone. 10 on 11.5. Melissa was asking a question. 10 on 11.5. On 11.5. Oh yeah, Melissa. I saw that, but by the time I respond, somehow my computer acted weird. So let us go back to 10 and 11.5. Let's go back there. Okay, let's just decide. Share an application, sharing an application window, chat session, share. Okay. Now you all can see the PowerPoint, right? I just want to make sure because this is like acting a little bit weird for me. So. Then A you were talking about, right? Melissa, let me check. Again, there are too many graphs in this 11.45 and 11.46. Yeah. Oh, total there are 6 graphs. You don't need to do all the 6 graphs, guys, if you are listening to me, because I'm sorry, I cannot see the chat session at this point. Just like 3 or 4 or something like that, you do it. There are 6 graphs. That is too much work. You don't worry about it. Okay, let us look at 10A. Again, I cannot read the chart session at this point, so I will do this and then I'll go back to the chart session. This is 10A. Let me check, unless you want me to work a specific example or. Okay, Lisa was asking something. Example from the reading. Okay. Let us look into this. 11.45a, I will work the closure for this. A, B, C, D, E, F. Again, once I'm done with this, I'll go back to the chart session and I look into it. The way you need to work a closure is this. I think they have given the explanation for on page 660. Okay. You take any two vertices which are not joined by an edge, and then you will add their degrees. If their degree is greater than or equal to n, then you will join them. So here in this case, n is the total number of vertices for 10A is 1, 2, 3, 4, 5, 6. N is going to be 6. And I'm just writing the degrees there. Degree of A is 1, 2, and 3. Degree of B is 1, 2, and 3. Degree of E is 1, 2, and 3. C is 3. D is 3. And F is 3. So I take any two vertices which are not joined by an edge, and I will, if that is greater than or equal to 6, then I'll add them. For example, A and B are joined by an edge. A and E, A and C. So A and D are not joined by an edge. So they are non-adjacent. So I'll find degree of A plus degree of D. I know that is 6. So I'll add a vertex between, I'll add an edge between them. So then this is what will happen. That is your first step. A, B, C, D, E, F. And then A is attached to B, C, D, E. The only thing is not F. Now you look into A and F. Degree of A plus degree of F is exactly again is 6. So that is greater than or equal to 6. So now I will join these two. That is the next step. You don't need to show each and every step. Now I will go to B. B is attached to A. B is not attached to C. So I'll find degree of B plus degree of C. And again, you can see that that is also 6. That is greater than or equal to 6. So I will join them. Similarly, B and E. That is the next step. Now, if you see that this is a complete graph because there are 6 vertices A, B, C, D, E, F. Degree of A is 1, 2, 3, 4, 5. That means it is attached to all the 5. Degree of B is 1, 2, 3, 4, 5. That is 5. And this is going to be degree of F is 1, 2, 3, 4, and then 5. Right? 1, 2, 3, 4, and 5. Yes. And so each and every vertex is now has an edge. That means is adjacent to each and everything else. So I cannot go further. So this is the closure of G. So you need to do 3 steps, but you can do everything in 1 step if you want. Now there is a result saying that if original graph is Hamiltonian, this is Hamiltonian because you are just adding edges, not vertices. So the Hamiltonicity depends on the vertices, not edges. If you can visit each and every vertex in the original one, you can as well do it in here. So that is the result, but the closure of G is this. You can do it for everything else as well, but don't worry that you don't need to do everything. You just do for like that, at least 3 of them, and then you can stop it. Any 3 is fine for me. Because I didn't realize there are 6 things you need to sketch, but that's okay too. You can do 6 also, but I'm saying that is not a big deal. So that's the closure. So for example, in this particular problem, You know this is Hamiltonian. This you already do that. You can do A, B, D, F. This is Hamiltonian. And A, I can start from A. I can go to B. I can go to D. I can go to F. I can go to E, and I'll come back to A. So A, B, D, F, E. Sorry. Then I can go to C and A. A, B, D, F, E, C, A. So the original graph is Hamiltonian circuit. So I can follow the exact same thing in here. So closure are also Hamiltonian. Sometimes you look into the closure, you will find the Hamiltonicity. The original one is also Hamiltonian. So just draw for couple. You don't need to draw for everything.
I have a question.
Yes, sir.
So do you have to keep adding the edges until they all have 5? And that example.
No. Not all have 5. You need to keep adding that. Now, if you take any two non-adjacent vertices, if their degree is say greater than or equal to 6, then you need to add. For example, I might have something in here. For example, I'm just modifying 10A, guys. I had an F, I had a say G here, and I have one more like this. Now degree of A is 3 and degree of G is 1. So degree of A and G is 4. It is not greater than or equal to 6. So you don't add an edge between A and G ever. So the degree of G is not going to go improve at all, because for example, degree of B and degree of G, degree of 3 is, this is 3 and degree of G is 1. So that is 4. That is not greater than or equal to N. So you are not going to add an edge. So each and everything will not be equal to 5. For some, it will be. It is a complete graph on 5 vertices. Sorry, 6 vertices.
Like
Sometimes it will be a complete graph, sometimes it will not.
I guess I don't, on your example that you made, the degrees for C, D, E, and F, aren't those just 4, not 5? Or do you actually have to add those, like keep adding edges until you have 5?
Which one you are talking about? The original one or the one?
The one
Okay,
where you
so-
started adding edges. Do you need to
Yes.
add an edge? And then from so that every single one has 5 and then it's closed?
No. You will only, that's what I'm saying. It need not be work alike all the time. All you are doing is, if in the original graph, if they were non-adjacent, that means, for example,
Right.
A and B are non-adjacent, you will look into their
So-
degrees and you will add them. If there is more than the total number of vertices, then only you will add an edge between them. If that is not, then you just leave it. You don't care about it.
So should there be an edge from E to D and F to C?
Oh, which I didn't do it. Yes, E to D, because 1, 2, 3, 4. Yes, there should be an edge between E to D for sure. And what is the next one I'm missing? F to C.
F to C.
You are right. Yes.
Okay.
Yeah.
And then they'll all have 5.
I thought you understood. Then it will become pi. Yes.
Okay. That's what I thought.
Yes. I'm sorry. I didn't finish it. Once I thought you got it, I guys just left it. Yes. You are absolutely correct. Yes, I think Melissa is also a little bit confused for that. Yeah. I'm sorry, since Melissa doesn't have this microphone, so I need to come back to the chat session. So once I use the PowerPoint and I'm writing it, it occupies my screen completely. So yeah, thanks for asking that, man. I appreciate it. Now, any other question, guys? Again, I'm recording this, so I'm going to post this also. Yes, as Melissa, we did both of them. Let me go back, 14 and 15. This is for problem number, in problem number 14, Melissa, this is what you need to do. Okay, I'm going to explain it in words. You can write it in your own words. Let me check if those are the only questions you have. No, that is fine. I can review for 1 minute for you. That's not that big deal. Don't worry about it, because so that I can answer your questions. I know the rest of the people can hear it once more. Yeah. In problem number, if you look into problem number 14, in 11.5, 11.3, I am sorry. Where is this problem? Oh boy. Yes. In problem number 14, this is what you need to do. Again, I didn't write the entire proof. I just explained in words, and you can write it in your own way. Suppose this is the digraph. I'll call this is the digraph D, and it has no isolated vertices, so this is completely connected. And it has a closed Eulerian path. I'll call that path as P. That means I can start at a point and visit each and every edge, and I'll come back to the same vertex. Now, to prove this is strongly connected, you need to take any two vertices U and V. You should be able to prove I can go from U to V, and also I can come back from V to U. So all I did said was, if you want to go from U to V, take that closed Eulerian path P and select U, because this path includes each and every edge. So it should include each and every vertex also. So U should be a part of that path. Sorry, circuit. Maybe I'll call circuit as C if you're confused instead of path. So I'll start at U and keep traveling on the Eulerian closed circuit. And I know at some point of time I'll hit V, because it is passing through each and every edge. So it is passing through each and every vertex as well. So I'll start at U and follow the closed path, closed Eulerian path. I'm too lazy to write. Closed Eulerian circuit, I apologize. Until I hit V. Then you start at V and keep following and until you hit U. Because this is possible, because this is closed. You are starting and ending at the same spot. So the picture is going to look like this. I'm starting at U and coming back to V, and I'm starting at V and going back to U. So I'm going to get a connection from U to V and also V to U. And if this is not closed, I might be able to do only one side but not the other. That is what happens in 15. This is the proof here. U and V are any two vertices in D, and now it has an Eulerian path. I'll call that path as P. That means I'm starting at a point and visit each and every edge and end up at some other point. I might not end up at the starting point. Now you take any two vertices U and V. I should be able to show you I can go from either U to V or V to U, sometimes both. So I'll start traveling in that path. Whatever is the first vertex I'll find, I'll either find U or V. One of them I'll hit first. Suppose I hit U as the first. Start at that point and keep traveling until I hit V. And now take the portion, this portion from U to V, from the Eulerian path. That is going to give you the connection from U to V. I might not have from V to U. That's okay, because as long as I can go in one direction, that is good enough to prove that is unilaterally connected. So take any two vertices, start traveling on the path. Whichever the first one you see in that path, that is where you should start. U be the first vertex you encountered among U and V in P. Start at U and follow P until you reach V. Take that portion of P which will use a path from U to V. I know I little bit went really fast here, but that is what 14 and 15. If you want me to explain it further, just type it on the this thing. Okay, is that making sense, Melissa? What about the others, guys?
I have a question about going back to 10 and all the different examples. Are there certain
Okay.
examples that are already closed?
Oh, if they're already closure, then CG of G equals to G. That might happen too. Which one you think is already closed?
Like the wheel-looking one, it's letter B in 1145. There's no adjacent ones that will combine degrees to be bigger than 9.
No,
right?
not you need to look at non-adjacent ones, not adjacent ones.
Right. There's no non-adjacent ones that will combine to be greater than there's 9 points, right?
Yeah, let me check. 1, 2, 3, 4,
All of
5.
them are connected to the middle, so if you pick any of the outside ones, they would just have 3, a degree of 3 with another degree of 3, which is only 6, correct?
Oh,
So-
yes. You are not going to take the inside one because that is connected to everything. You are right. CG of G is same as G.
So is that one that is technically already closed?
Yes, you are right.
And then that kind of leads me to like the next one, C, which is like a box-looking one.
Mm-hmm.
Each one has either a degree of 4 or I guess there's 4, 3, or 2. But none of the ones you pick will be able to combine greater than 12, which is how many vertices it has.
Exactly. That is what you need to figure out rather than trying everything. That is a great job you are doing. Because the degree of A is 2, the degree of M is 2. Yes, the degrees are either 2 or 4 or that's it, right?
Like C is 3, or not 3. E
Yeah,
is
C is
3.
yeah, the degrees are either 2 or 3 or 4. So if you add any 2 degrees, the maximum you're going to get is 7, which is certainly much less than the 12.
Right.
So that is also closure. Yes, you're right.
I just wasn't sure, like, because I was kind of looking at them and it didn't make sense that I was looking. More of them seem closed initially than ones that you had to fix, if that makes sense. They just seem odd.
Oh, hope that is the case. In that case, you are lucky, right?
Yeah.
You are right. I think B and C are, yes, they are like that.
Okay. I just wasn't sure if I was doing it right or not, but okay.
Oh, yeah. I think you helped a lot of people in the section also. That is good. Yes, you're right. I haven't done all of them. I did like one and I did one there and then I decided, okay, this shouldn't be too bad. I think you can figure it out. So, oh, yeah. Yeah, you can do only 3, Melissa. That's fine. Again. Any more questions, guys? Okay, sure, James, you can leave. If you have no questions, you can leave, guys. If you have any questions, please either tell me or do the chat session. If you have no questions, then I will shut down the session.
Thanks.
Oh, no problem, man, no problem. I'm going to post this video, I think in 1 hour or 2 hours, I think it will be uploaded. You can look into that. Sure. No problem. Okay, it looks like none of you have any questions, then I am going to take off then. Thank you, Nisa. Thanks a lot. I want to stop sharing.